Hello guys, you are welcome to the Jamb 41's YouTube channel. In this video, I'm going to deal with certain terms that are used when studying wave motion. Terms that are used in describing wave motion. Some of these terms include amplitude, wavelength, frequency, period, cycle, otherwise known as revolution or oscillation. And then we have that which we call the phase. This video lesson is very important because in the study of the concept of progressive or traveling wave, there is this mathematical equation that defines this traveling wave. It's very important for a student to know how to apply that progressive wave equation to solve problems. An examiner can use that equation to try you on the aspect of calculating any of the following terms that is used to describe wave motion. Alright, so I'll quickly define these terms and then you're going to get to know about the formulas for these terms that are used to describe wave motion. Before then, I'd like you to please take a look at what our progressive wave looks like. Alright, so this is the graphical representation of the progressive wave or traveling wave. Now that you've seen this graph, I would like us to now define the terms that are used to describe wave motion. The first we're going to define is the amplitude of a wave. What is wave amplitude? This is defined as the maximum displacement of a wave from its mean position, from its rest position. That is what the amplitude of a wave is. I'd like you to take a look once again at this graphical representation of our progressive wave. Now you notice that there is a sinusoidal waveform shown. Okay, the graph is a sine graph. And then along the vertical axis, the y-axis, okay, you could see that the graph stretches upward to a certain height, the peak, and then curves downward. Getting to the minimum point, it still curves upward and it continues that motion in that format. The highest point, that peak, traced to the vertical axis, is what we call the amplitude. Now, the wave initially is considered from its source, where the wave is being generated, is considered to be at rest, the mean position, the rest position, which of course is represented by the horizontal axis. You know, your vertical and your horizontal, so you have where the vertical and the horizontal meet. Usually in plotting graph, that point is given as 0. So by the time you set a wave in motion, the maximum displacement you give to it, which is the rise to that highest peak. Are you following, right? The rise from that origin, that rest position, to the highest peak. That is what we call the amplitude of the wave. Once again, the maximum displacement of a wave from its rest or mean position. Now this is about displacement, and so we expect the SI unit of amplitude to be meter. We use capital A usually to represent the amplitude of a wave. Let us now define the next term that is used in describing wave motion. We are going to talk about the wavelength. Wavelength. Now you could hear about the term length. So definitely what will come to our mind is the length of a wave. By definition, wavelength is defined as the distance between two successive crests, or the distance between two successive troughs. Now when we hear about the crest and the trough of a wave, what does that mean? Once again, look at the screen. In this progressive wave graph, now we have the peak, the maximum point, and then it gets down and curves upward again. That down point is the minimum point. As the graph moves on, it curves again at another maximum point, okay? So the maximum point, that peak, that top, that top of the graph, are you getting me right? The maximum point, yeah, is called the crest. Then the minimum point where the graph, gets down and turns upward, that minimum point is called trough. So if you pick any two crests, the distance between it, the length from one crest to another crest, is what we call the wavelength. Or simply, the length from one trough to the next trough is what we call the wavelength of a wave. Once again, wavelength, like the name goes, length, okay, would have the unit of meter. Because here we are talking about distance once again, okay? Now, wavelength has this relationship with frequency. It also has this relationship with the velocity of a wave. And mathematically, the wavelength of a wave related to the frequency and the speed of the wave, or the velocity of the wave, is giving us wavelength, which is lambda, we use lambda to represent it, equal to the velocity v of the wave divided by the frequency of the wave f. Now, when we are talking about the electromagnetic wave, that velocity v is equal to the speed of light, which is 3 times 10 to the power of 8 meters per second. Take note of that. If the wave is an electromagnetic wave, gamma ray, X-ray, ultraviolet ray, visible ray, infrared, and down to radio wave, that velocity would be equal to the speed of light, 3 times 10 to the power of 8 meters per second. But if you're dealing with other, types of wave, perhaps mechanical waves, that V does not have a specific value as it could be. Are you following, right? Let's say you talk about the wave generated in water, which is water wave, or you talk about the wave that is generated in a spring, alright, or in a stream. It will have its own defined velocity, which is not the speed of light. Alright, let's look at the next term that is used in describing wave motion. We are going to define the frequency of a wave. The frequency of a wave is defined as the number of cycles that is made or covered by a wave in 1 second. Once again, the number of cycles that a wave covers in 1 second. So clearly, it is obvious that frequency is simply about number of cycles. As the wave is traveling, take a look once again at our graph. As the wave is traveling from one point to another point, how many cycles is it covering, okay, in 1 second? That defines the frequency of the wave. And I'd like to say this, please, as you move from one crest to another crest, or from one trough to another trough, you cover a cycle, right? So in a wavelength, you have a cycle, another wavelength, you have a cycle. So how many of these cycles are being covered? How many revolutions are being made in 1 second? That gives us the frequency of a wave. Don't forget, like I said, frequency is simply number of cycles, but relate it with time. Is that okay? And mathematically, from that definition, frequency f will be equal to number of cycles, I'm going to use small n for it, divided by time, small t. Take note of that. We are still going to see another formula, alright, for frequency, which connects it with period. But I'd like us to define period first before we talk about that frequency formula. Is that okay? The unit of frequency is hertz. Hertz. You could also have the unit per second. That is inverse of second. Is that okay? Let's move on to the next term using describing wave. We're going to talk about the wave period. Okay? So what is the period of a wave? The period of a wave is defined as the time it takes a wave to cover 1 cycle. How long will it take a wave to make a cycle, to complete a revolution? That is what the period of a wave is. Now, from that definition, once again, it is clear that when we talk about period, remember the time it takes. So it simply means that period is time. So what time will it take for a wave to complete 1 cycle? That gives us the period of a wave. Now we use capital T to represent the period of a wave, and of course, mathematically from that definition, time taken to cover one cycle, we could say that period capital T is equal to small t divided by n, where that n once again is number of cycle. What is the formula for period? Like I said, when you relate it to frequency, remember period on its own, capital T is small t over small n, where the small t is time, and then the small n is the number of cycles. Are you following, right? Then you recall that in defining frequency, mathematically we expressed frequency to be equal to number of cycles, n, divided by what? T. So you see that there is this relationship between the frequency f and time, that is a period rather, capital T. Take a look at the two formulas, please. Frequency is n over small t. Period, capital T is equal to small t over what? N. You can see that the frequency formula and the period formula is simply inverse. One of them is the reciprocal of the other. Okay? Frequency, n over small t. And then period, capital T, is small t over n. So it's as if you turned that frequency formula upside down, right? And inverse. Therefore, there is this relationship between frequency and period you should know about. And what is that relationship? If you multiply frequency times period, it's going to be equal to n over t times t over n, which of course will be equal to 1. So frequency times period is equal to 1. Therefore, frequency is equal to 1 over period. And that is how we got to know again that another unit of frequency is per second. You want to take note of that. Let us now define wave speed, or velocity as I call it. The speed of a wave, as we know generally from the concept or the study of motion, is simply the distance that the wave covers in a given time. That is what the speed of a wave is. Distance that the wave covers in a given time. Now I'm going to use V to represent the speed. And mathematically, as we may have known, that speed is equal to distance over time. Permit me to use x for distance. If you cross multiply this equation, if speed v is equal to distance over time, that is x over t. If you cross multiply, you get the distance x to be equal to vt. Please take note of this. These equations that I'm establishing as obtained from the definition of these terms are very important because when we establish the formula for progressive wave equation, you will see how we are going to use these basic definitions and their formula to obtain that progressive wave equation. Alright? So follow along please, because my next video I'm going to be releasing that video lesson on progressive wave equation, and I'm going to be making reference to all these formulas I'm establishing based on the definition of these terms used in describing wave. The unit of speed is meter per second. Remember that. Let us now define cycle. Cycle. Simply put, cycle is the number of oscillations, alright? The oscillation that is made, the revolution that is made by a wave. We can relate it to the concept of phase, which I am going to now define. Is that okay? The phase of a given wave. And sometimes you can hear it about, you may hear of it as a phase angle. Alright, P-H-A-S-E. So what is the phase of a wave? I'm going to define that, and I hope you are ready to follow up. The phase of a wave is simply the state of vibration of that wave. When you talk about the phase of a wave, we try to find out, okay, is the wave at its maximum point? Is it at its minimum point? Or is it at its rest position, which is the 0 point? Of course, we use theta to represent, alright, angle theta. Like I said, it goes with the concept of cycle. Are you getting me right? We use theta to represent this phase angle. We use theta to represent it. And I'd like to say this quickly, please. From the study of circular motion, we talk about angular displacement theta. There is this relationship between angular displacement theta, as we use there, alright, and angular velocity, also called angular frequency, omega. Under circular motion, if we know generally that velocity is displacement of time, then angular velocity will simply be angular displacement divided by time. Now angular displacement is theta. So you take a look at this, we have omega w, to be equal to theta over t. That theta is angular displacement. If I make that theta our phase angle subject to the formula, theta will now be equal to w what? T. That is omega t. Don't forget this. And to wrap this up, remember that our angular velocity, also known as angular frequency, is equal to 2 pi f. That is 2 times pi times frequency of the wave. Please, dear friends, make sure that you watch this video lesson, grab the definitions given and their formula of the terms used in describing wave. Very important because, like I said, in my next video lesson, we are going to treat the progressive wave equation. Please watch the screen as that equation displays. Perhaps maybe you have seen the equation before, or this is the first time of saying it. How was this equation generated? And I'd like to also say this, that this is not the only form that the equation can take. And that is why the next video lesson you would not want to miss it. If you are yet to subscribe to the Jamb 41 YouTube channel, please do so right away. Follow along, turn on the notification bell, personalize your subscription so that once I upload any content, you will be personally notified by YouTube so as not to miss out. Is that okay? So like I said, the next video lesson is going to be a super one as always. We're going to derive the progressive wave equation and then make use of it in solving problems. You're going to see the different ways in which that equation can take, because your examiner decides whichever form to use in asking you questions when you are seated in your exam. But remember this, to understand the progressive wave equation, you have to make sure that you watch this video lesson again and again, understand the definitions given, learn the formulas, because these basic formulas are what we're going to use to play around obtaining the progressive wave equation. Alright guys, I'll see you in my next video lesson. Don't forget, you can become the Jamb 41's channel member where you get exclusive benefits, especially for channel members. Simply tap the join tab that is below this video lesson and of course choose whichever package that is convenient for you in order to become a channel member and you get even much more benefit. Alright guys, take care of yourself and share this video lesson to others as well.